All right. So I'm recording this. I think a lot of people are interested in forecasting and they think they know what forecasting is, and they have maybe had a basic class in it, and everybody's familiar with like weather forecasts and whatnot. And principles are very similar or the same mathematically to all the stuff that people are familiar with. But um, I wanted to specifically talk about a couple of things that are slightly more advanced topics in forecasting, which are the seasonality, which is not just like the seasons of the weather, right? Like winter or summer, spring, fall. It has to do with how the patterns in the data can be projected out in the near or long future at various different time intervals. So you can forecast throughout the day, you can forecast throughout the week, through the month, or even at a time interval that maybe people aren't even familiar with, right? That doesn't correspond to like an Earth Day time measurement. So you can get into some really weird pattern fluctuations in data around forecasting related to seasonality. And there's a lot of different ways to adjust for seasonality. Um, like the biggest example that most people are familiar with is just Black Friday, right? With buying patterns with shoppers every year, there's a seasonal pattern the day after Thanksgiving because of this unnatural holiday that's been created in the United States. There is a huge buying spree that everybody goes on because they get done eating their turkey and then they realize they got to buy all their Christmas presents. So Black Friday started to take effect, I don't know, some point in the 50s or the 60s, I think. But there's a million patterns like this in seasonal shopping and in logistics and supply chain and in stocks. Like there's usually a bump in stocks at the beginning of the year, and then it kind of mellows throughout the summer and the fall, and then it starts to sort of like see a bump at the end of the year. So there's but most buying and selling patterns with stock have adjusted for that over the last 50 years, and so you don't really see it in the prices anymore. Now that being said, I'm going to show some of the basic forecasting stuff just to give additional context for the seasonality. Okay, forecasting, planning, and goals. There was a specific page here that had some cool charts on it. That some basic steps, time series patterns. All right. So this was a chart that I thought this book, by the way, if you're interested in this subject, this book is like a comprehensive forecasting 101 book that if you understand the principles in this, you will get you very far in managerial and executive level like knowledge. Like if you can do this stuff on a basic basis, then you can you can predict and understand what's going on around you to a much greater detail. The finance guys do this all day, every day. I mean, they're constantly just aggregating data and putting data together and trying to forecast the 3, the 6, and the 9-month projections. The sales guys have to do this to a limited effect, but they're really just trying to figure out, how much they think they're going to be able to sell. It's one of those tools that, like, no matter what job you're in, if you're in a leadership role, you should know how to do some forecasting, at least at a superficial or basic level, right? So here's some time series patterns, and you can see just with the naked eye, there's some pretty clear patterns associated with, this is like home sales. You can see that there's clearly a multi-year pattern associated with home sales and an internal year pattern. There's basically two patterns overlaid inside of each other here that you can kind of see. And it looks like that's every other year is one of the patterns. And then it looks like there's a 3 to 5 year pattern where it goes up and then down again. So there's two seasonal patterns associated with home sales. Kind of curious where we're at now that I'm looking at that. And then U.S. Treasury bill contracts, there's, ups and downs. This one is a little bit fascinating, the Australian quarterly electricity production, because you can just see the growth of electricity production over time. But the it looks like my guess is these little bumps are the summer and or the winter, one or the other. Like the electricity production bumps up to, do additional heating or cooling. And then I don't see anything in Google's stock price daily changes, other than it looks like on day 600, they probably finally had some good news and exploded. If you were to overlay this with the actual dates, I'd guess that this is where Google finally came into the news in a big way. All right, seasonal plots. It's not particularly useful for demonstrating. So this is focused mostly on monthly, but polar seasonal plots. Anti-diabetic drug sales. So this is drug sales around diabetes. And it looks like over the years, they've sold more and more diabetes drugs. I don't really like that chart. Forecaster's toolbox. So simple forecasting methods. This is, there's some math here, but I'll skip the equations just so you can see it on the chart, because it's really easy to understand when you look at the chart. When you look at these formulas, it's a little overwhelming. And it's, it's a lot of algebra, sometimes calculus, but don't bother, I guess is my point, right? The guy who did this, Rob Hinman, he's a genius. And he's, if you really want to start working with this stuff, you just end up, downloading the R packages associated with these various methodologies, and it's a formula you just plug, some variables into, and then it spits out a chart for you. And the chart is really what ends up mattering the most, because you really want to know what these blue, red, and green lines are over here. This is what you're trying to predict. So this would have been run in like 2006, 2007. And they're trying to figure out what beer sales are going to be. And he's got 3 different methodologies basically projected on here. The mean forecast is what most people are usually used to, or mean drift. But it basically just takes an average of all the historical data that you have available, and then just takes a line and puts it straight out. The naive methodology takes the latest, the most recent value that you have available to you, and then projects it out. So you can see where the latest they have was up here. So they projected that out. If the latest had been like somewhere on the downside of one of these spikes, they would have just projected that out. But the reason it's called naive is because it's just such a simple, well, it was 25 yesterday, it'll be 25 today. It's just such a simplistic methodology. And then seasonal naive basically uses one of these formulas to calculate the bottoms and the tops of the peaks, and then the rate of change between those peaks on the intervals, and then just kind of maps it out. So seasonal naive is also fairly simplistic, but gives you a much better idea than mean or naive. And they're all, easy to learn methodologies that you can do really, really quickly. And then when you want to get into a slightly more sophisticated forecasting methodology, you start adding drift into it, which basically accounts for the general trend, the slope of your data. And then you adjust all of these based off of the slope of your overall data set, right? So if you were to adjust for the slope of this data set and add drift into this, what you would see is that the peak on this second little blue spike here would be lower, right? And the bottom of this third bottom spike would be lower, right? Because the overall slope of this average data set is downwards and trending. So that the seasonal naive would be sloped downward if you added some drift. So here he talks about some of I think he talks about drift in here. Oh yeah, cool. Looks like he embedded a chart that we could play with. It's not working. All right, so this is another really important part of all this, which is evaluating your accuracy on your forecast. So after you develop whatever, formula it is that you're using to like determine what the values are going to be for like the next, we'll say 3 months if you use monthly data. After you develop your formula that gives, you plug your historical data into it, it spits out a value for month +1. You take that data, you take 1 month off of the top of it, and you use it to project the 1 month that you do have progressively backwards in time. And what you get is you get a variance, like your model variance. Let me see if I think I actually did this relatively recently. Maybe I could pull up an example, but basically you use your data set of actuals to evaluate your model's accuracy, and you get an error calculation. Like, okay, so when I applied my model to the data set that I know exists, I have the actuals for April, and it says it's supposed to be 35. Well, I plugged my model into it, and the model says that I'm supposed to have 30, so it was off by 5. And what you do is you apply that across the entire data set, and it gives you a variance allowance across all the data set. And then you add it all up, and like, how big is my variance on this model? And then what you try to do is minimize that variance across all of them. So maybe I can find this example. It makes a lot of sense when you see it in Excel. Yeah, I don't have it. I was hoping I had an easy example right here, but I don't. All right, yeah, so this is where he's talking about the forecasting error. And again, don't worry about the math. It's not that important. I know that sounds stupid, but all right. So here it is. Here it is on a chart. Seasonal naive, you can see where he kind of did the forecasting adjustment. All right. So most people, this is the mean standard error, mean average standard error. It basically is taking his forecast, applying it to the historical data, and then calculating that out. Yeah, there it is. All right. So the following diagram illustrates the series of training and test sets, where the blue observation form the training sets and the red observation form the test sets. So this is over time. So like so imagine these are months: January, February, March, April, May, June, July. So in June, this is your, your test sets, or sorry, blue is your training sets, and red is your test set. And so this is the month that he's doing that is April, May, June, July, August, September, October, we'll say. So this would be getting done in November. You're using everything prior to October you would use. And so the last month that you have available actuals on is the data that you use for your calculation. And you do this on every single, this is the entire data set, right? This isn't like a point in time. You would look at this on entire data set. So you basically would take your model, use the model to calculate this month, get your calculation, use it for this data set, calculate it for this value, and then what you do is you aggregate all of that together to get what the average red dots are off by, right? And you're comparing the red dot forecast to the red dot actual. So you're like comparing these two here, right? Because you do know what the actuals are, but you're using the data that you have prior to that to calculate your forecast for it. Does that make sense to everybody? It's conceptually difficult. Once you get it though, it makes a lot of sense. Let me see if I can, here. I'll just make a data set real quick. It takes 5 seconds. All right, this will work. Let me share it here. All right. All right, so here is a data set, right? So we're going to sort this by date. And then you can see I've got some rough data in here, right? So a lot of times with these kinds of things, the first thing you end up having to do is like clean up your data. And so I'm missing data for some of these dates. So the first thing I'm going to do is just like fill them in. And because we're doing forecasting, we already know that the data is always going to be somewhat questionable. So, and you use the data you have. It doesn't matter how good or bad it is. Right? That's why it was sorted by amount. So I've got a bunch of blanks, a bunch of zeros. So what I'm going to do is I'm going to take the average of the values that I do have. All right. And then I'm just going to fill it in because I want this data there, but I also don't want it to be impactful. If I left all zeros, it would just drag down my averages and my values, right? So it's going to make the data look bad. So I'm better off just filling it in with an average value so that it doesn't screw up my calculation. Some people would frown on that, but for the purposes of this, and honestly, for the purposes of most forecasting, you end up doing that kind of thing a lot. As long as you're tracking what you're doing or why you're doing it, it's not a big deal. So now I know this is the average value, and if I see that, I know it wasn't blank before. All right. So then, sorted by date again. And I would do this if I was in a more sophisticated, thing. I would fill it in. I'd make sure it was on a regular interval. You can see like I would have this set up to where it was every day or once a month, and I would put it on the same date, right? But you get the idea. I have a time interval. We'll say it's monthly, right? And I have a value associated with it. So now that we have them in order, right? Let's say that we're going to try to predict this value here. Actually, we're going to try to predict one of these values down here. You basically come up with a formula that says, listen, the naive method is just, here's my forecast. Right? These are my actuals. This is my forecast. Naive just says, give me your last value. Right? 1 month early, or was this? That's what it's going to be this month. So here's my naive. My last value I got. All right, there's my naive forecast. It's literally that simple. This is the last one I got. This is what it's going to be next month. When you get into more sophisticated methodologies, you might say, well, I want a rolling average, right? So I'll say you need at least 3 months worth of data. It's going to be the average of the previous 3 months. See? So September, my forecast for September is going to be the average of the previous 3 months. This is another relatively naive methodology, but you can see how it gets you a different value for your forecast. All right. And I'm going somewhere with this, bear with me. So now I've got two different forecasting methodologies here. Get rid of that. All right, so I've got two different forecasting methodologies here. Now, question is which one's better? Which is a better methodology for forecasting what the service amount is going to be in the next month, right? Well, how would you judge that? Well, you want to get a total accuracy of each one of these forecasts, right? So you need a variance. What's the variance between each one of these forecasts and what the actuals ended up being? All right. So it's kind of unfair to compare the two in these first couple of months because I don't have enough data to even do a rolling average forecast for this first couple of months. But the calculation is really easy. These are what my actuals were. This is what my forecast said it was going to be. So what's the variance here? So it equals this minus this. So there's my variance. There's my forecast. There's my actuals. There's my variance. So how off are they overall? So you can look at an individual forecast, right? And take a guess of how much they're going to be off, right? Like this one was off by 487,000, and this one was off by 2.5 million or whatever. But it doesn't matter because we're going to use the average standard error. So this is the error. There's different ways to judge how accurate a model is too, by the way. But we're just going to compare these two. All right, so for this one, for the naive, it was off by 14,586. And for the rolling average, it's off by 229,000, right, on average. So when you look at these superficially, it looks like the rolling average is a much more inaccurate way of doing a forecast, at least for this data. Does that make sense? So you just keep on coming up with new formulas to do your forecast 1 month, 3 months, 9 months, but you're only allowed to use the data for the actuals that you have prior to determine how accurate that model is. All right, so my forecast would have told me if my forecast for my rolling average methodology for January 10th's deliverable would have given me this value. All right. It's a pretty important principle in forecasting. Once you understand it, it makes life way easier. And it's the same principle that's applied for developing any sort of model, whether you're trying to categorize something or if you're trying to, build a neural net or a machine learning thing. The principles are the same. They're all statistical model development methodologies. And then once you have this formula, then you can take it and throw it into a function and then create a piece of software out of it that actually does something cool. All right. So going back to Hinman here. you can see how he's talking about how to evaluate the forecasting accuracy. He talks about, this rolling average, and then, this is a 1 month forecast. This is a 3 month forecast. He's trying to project 3 months out. And then there's a bunch of stuff about how to use R. Mean standard error is what he's talking about. And you can see this is an explanation that if you apply a model that was developed for a 1 month forecast and you apply it to a 2, 3, 4, 5, 6, they get progressively, then MSE gets progressively worse. So where does this come into for seasonality? So seasonality is just an additional complexity added to that formula to account for drift, or to account for the pattern you see over time in the setup data, right? And the easiest way to do it, in my experience, is you add another table somewhere as a variable. Get the idea, that says, all right, in my formula, I want you to look up what month it is. And if that month is January, regardless of what methodology I'm using, I want you to add 30, because I know that it always goes up by 30 in January and it goes down by 20 in February. So you basically build out your seasons, right? And in this case, we're saying that a month is a season. You could just as easily create, fall, summer, fall, winter, spring, summer as variables that you plug in. All right. And then you just use it as a lookup table from a seasonality perspective. And you say, listen, I know that it's January, so add 30. I know it's February, so minus 20. But it's also winter. So the winter months, you add, plus 50. Whatever. Make sense? It doesn't make sense to have multiple seasonality, things like this, that are corresponding to the same interval that overlap, right? So fall corresponds to 3 months, January, sorry, what is it, August, September, October, or September, October, November. Yeah, September, October, November are fall. So you wouldn't have September, October, and November on here, and then also do a lookup for fall. You would either use fall, or you would use the more granular version, which is the month, right? But so and vice versa, right? Like if you were doing seasonality, but you had day of year available, you wouldn't use month or the actual season. You would just use the day of the year associated, because it is a subset of one of these already existing larger sets. Now, if you can't get down in your data set to that level of granularity for your seasonality calculation, then yeah, you use the January value. And if you can't get to the month, then you use the fall, or you use the actual season. But this also corresponds with economies. Actually, economics is really big on this. And then they actually use an even larger subset, which is like, there's the year seasonality, right? 2020. There might be, characteristics related to a specific year pattern that need to be taken into account. Maybe it's that, odd years, there's, even years, it's plus 20, and odd years, it's minus 10, whatever. And then there's even a bigger one, obviously decades. You see how it gets more and more granular, more and more whatever the opposite of granular is. And when you're developing a model, you always want to go to the most granular thing that you have available that is applicable for your seasonality pattern, right? All right. So seasonality makes a big difference on all this. So where does this all come in for logistics and the bullwhip effect? So, which is really what I kind of wanted to talk about, but you have to understand forecasting, you have to understand seasonality before you can talk about the bullwhip effect. So the bullwhip effect, you know, I found a good basic article that kind of explains the bullwhip effect on it. So the bullwhip effect, it basically amounts to how much stock you have of whatever it is that you're selling or building, right? And it applies to pretty much any kind of manufacturing process or any kind of like anything essentially where you're trying to build things out and ship them out the door. But you have to maintain a set of stock in order to either build the thing or to just have available for shipping just in time for when it goes out, right? So the way you do that is you forecast how much you're going to need, right? I know that in every month I ship at least 100 units. So you keep 100 units on the shelf. You always build 100 units because you know that you're going to sell 100 units. Where it gets sticky and where the supply chain functions come into play is that you might need 4 different types of widgets, right? In varying amounts in order to build your final product. So you have to keep on stock in advance. They have to be there beforehand. Those 4 different type of widgets in the correct amounts in order to manufacture your final product. So in a one-step supply chain, that's not that big of a deal, right? I ship out laptops, I order laptops, one step. I know I'm going to ship out 100, so I order 100. It gets more sophisticated when the supply chain is more extended, right? How many steps are there in the supply chain? Well, I know that my final product requires an operating system. It requires a custom software installation. It requires a power cord device. It requires a Wi-Fi attachment. You got a laundry list. You got 10 different things that all have to be there at the same time to go out the door together. If you're missing one component, then it starts to fall apart. And each one of those components has a dependency of, 3 or 4 things. And each one of those components. So you see how it builds up very quickly, the complexity in a supply chain. And the bullwhip effect basically is an explanation of this overestimation or underestimation that is the result of forecasting methodology. So I suspect because of seasonality that on Black Friday, I'm going to ship an extra 4,000 units. So I'm going to order an extra 4,000 units. If the person in front of me in the supply chain hasn't also accounted for Black Friday in their seasonality, they will not have that 4,000 extra units on stock or the 4 different widgets required in order for me to make that 4,000 units. So the forecasting methodology, basically the way to reduce the bullwhip effect, is to make sure that every single step in the supply chain is fully aware of your forecast of what you think is going to happen coming up. The least accurate forecast causes the highest amount of bullwhip effect. So if you wait a day till the day before to figure out how many things you need to ship out the door, what happens is the guys earlier in the supply chain have to scramble to figure out how many of their item they need, right? So short version is the longer you wait to figure out how many you need to meet your commitments, the harder it is for the people before you in order to adjust for that. And what it causes is the farther in the supply chain, the worse the forecasting is farther in the supply chain, the more stock and the higher inventory the earlier steps of the supply chain have to hold, right? So, and it's a multiplier effect. So 15 units, as you can see here, 15 units forecasted by customer demand. So the retail has to stock. Well, they know that the forecasting is not perfect because no forecast is ever perfect, as you just saw. So the question is how many units should they keep on stock in order to adjust for the fact that the forecast for the next step is bad, right? They say 15, but I don't believe their forecast. It's really going to be 20 units, right? So the retailer says, I need 20 units. I'm forecasting 20. And the wholesaler, who's one step before that, is like, yeah, the retailer, their forecasting is always off. He's saying that the forecasting the customer is always off by 25%. So he adds 5%. Then the wholesaler says, well, yeah, but the retailer is always off by 33%. So I'm going to add an extra 30% onto mine. And the manufacturer, who is actually building whatever the widget is from raw materials, says to themselves, you know what? Those wholesalers are always off by double. So I'm going to double mine. And then the raw material developers, so the people digging the stuff out of the ground that we build it out of, they're like, man, I better increase production. So I better build another power plant and I better build another mining excavation methodology, right? So you can see how what is a relatively straightforward, forecast at the very beginning kind of explodes in this bullwhip effect throughout the supply chain and causes this exponential stockpiling of materials and devices and deliverables. And superficially, you're kind of like, well, yeah, but that's what they get paid for, and they build that into their margin. True, but it also ends up all of this inventory that sits at each one of these steps in the supply chain ends up being a huge sunk cost associated with that particular business, right? So those are assets that are sitting in a fixed form that they can't liquidate easily and can't use for cash flow, right? So it ties up millions of dollars of stuff just like sitting in a closet somewhere. So like in laptop businesses, like just warehouses full of laptop devices just sitting there doing nothing. It becomes even worse when you start talking about food chain supply, right? Because anything that's perishable, it gets even more critical that the forecasting be fairly accurate, because not only do you get this stockpiling effect, what ends up happening is the stuff that's perishable actually goes bad, and the value proposition for those specific items goes down over time. So like milk, everybody always is like, why are they pouring all that milk into the sewer when there's starving people wherever? Well, that's because the supply chain isn't capable of delivering it, right? The warehouses and the trucks associated with that delivery are full of already perishing other items that they can't use to get there. So the transportation system and the supply chain itself actually has a capacity limitation. So when you have a misforecast, you have this bullwhip effect that by the time it gets all the way back to the farmer, you have this huge amount of overproduction that essentially just goes completely to waste. To make it even more sophisticated and complex from a supply chain perspective, each one of these, right? If it was a simple, straightforward, well, why don't they just tell the step in front of them what their forecast is so that they can more accurately get their forecast? Because for every customer, right, the forecast is going to be completely different. It's very difficult to forecast on an individual basis. I can tell you I'm going to use about 2 pounds, 3 pounds of coffee month, and I'm being generous, probably more like a week. But now, if you were to ask me like how much is the United States going to use, well, there's thousands of different retailers, and then there's thousands of different brands of coffee, and there's thousands of different aggregators. So like even though you're a manufacturer, you might sell to 6 different coffee manufacturers, right? And then there's other complexities, like some of them are retail, some of them are restaurants, some of them are fast food that have very good accuracy, some of them are mom and pop shops. So forecasting at this level is incredibly difficult at the tail end. And the forecast for the retailer ends up having to be dependent on trying to predict customer behavior, right? So it ends up adding a level of complexity and inaccuracy from that, because who could have predicted some of the things that'll drive customer behavior, like, I don't know, a pandemic per se, right? And then the wholesalers, depending on the retailers. So you end up having a glut in wholesales as well associated with all this. And then it drives it all the way back to the original manufacturer, so like the milk producer or whoever. So when people are, what drove the price of this specific stock or this specific commodity? So like oil. I mean, oil is like the negative price on oil. How does the price on oil go negative? Well, people stopped driving, people stopped flying, companies stopped shipping. The demand for oil went just through the floor, right? It just disappeared. The people who sell it have a much reduced demand, right? So the gasoline companies, I'm just using them as an example, but there's tons of oil plastic producers. Everybody has a reduced demand for oil right now as a result of all the pandemic stuff going on. And then you go farther back into the chain to the final manufacturer, which you're talking about OPEC, Saudi Arabia, those kinds of guys. And then the shale companies in the United States. And they have to store the oil somewhere. Well, because people aren't buying it, it's actually filled up all the warehouses and all of the oil storage locations available. There's literally no place to put it right now. The problem is that if you shut those machines off, starting them back up actually is really, really expensive. More expensive than actually shutting, than just like storing the oil somewhere and buying storage for the oil that it produces, to a point. So what ends up happening is you actually end up paying other people to take your oil, because it's cheaper to pay them to take your oil than it is to stop producing it. And that's particularly true in the nuclear power plants. The nuclear industry is very, very much like that. Like after you hit a certain threshold, you'll see the price for nuclear energy go negative fairly often, actually, because you can't shut down a nuclear power plant. It's the same principle of the bullwhip effect. And it is basically completely ingrained in society. Most people, it's a concept a lot of people don't really understand. They're like, how do milk producers dump oil or dump their milk, and how do oil producers have a negative price on their oil? Well, here you go. Here's the explanation. It's the bullwhip effect. All right. Is that a good explanation for everybody? Any questions? Anything to add? I'm hardly an expert in all this stuff. I just want to highlight that. Adam, you're always good for input on this. I'm sure you've seen this before. Sorry to put you on the spot there, if you're even paying attention anymore. Candy, I know you see this all the time with your logistics devices you're trying to ship out.
Oh yeah.
You get hit with this all the time. All right. If nobody else has anything to add, then we'll go ahead and close it up. It's a fun topic. If anybody has any questions around forecasting or bullwhip or logistics, feel free to hit me up. We have guys that do this full time all day. The logistics department is particularly good at this. They've gotten increasingly sophisticated since I've been here. When I first got here, Cropper actually had a relatively sophisticated methodology for forecasting demand, which was a little bit more sophisticated than I expected, to be honest with you. And then the logistics department on the legacy CRF side has gotten, increasingly sophisticated since I've been here. Before, they weren't really doing any sort of sophisticated forecasting. They were just kind of like, whatever the orders are, we'll order them in advance and they'll sit in a warehouse. And it was a very, capital intensive way of managing it. Cropper's methodology was actually better. And then what happened is the new logistic guy, Richard, came in and he was like, well, we need to improve our forecasting methodologies. And so he started getting more involved and put together some logistics supply chain forecasting methods for that group. So they're getting better over there on a consistent basis. And Richard is really sharp. Some of the stuff he brings up is pretty good. So yeah, we do this here a lot. All right, well, if nobody has any questions or comments, then we'll close up shop and call it a day. Thanks, guys.
Thank you.